All right, so now we'll be discussing two paradigms. First is coordination, and second is strategy. So coordination basically talks about how do we optimize a fleet when one central brain controls every single move. So we explore this through the MAPF problem, map finding problem, and second is strategy, which we will be talking about in the non-cooperative game theory concepts, where we predict outcomes when every agent acts in their own self-interest. Right. So the centralized challenge is coordinated logistics. The application is routing a mixed fleet of over the urban networks. Agents are the trucks on ground, and we have drones in the air. So the synergy drones have limited energy, and they basically use trucks as a temporary transit method to extend their range. So they'll basically the drones would land on the trucks, and the trucks would actually be carrying them on their own routes, where basically during the journey, the drones would basically be able to charge themselves up, and then they can fly off when they're sufficiently charged. Now the goal is to minimize total vehicle distance while managing complex air ground synchronization. So why is this hard? The coupling problem. So we have loosely coupled standard MAPF. Here basically agents are rarely interacting and the conflicts are local. Then we have tightly coupled wherein we basically have the drone truck interactions. So the drone path is locked to the truck path, and there is zero cost during the transit, which makes it optimal path dependent. And interactability is we cannot plan for drones and trucks separately because the drone saves energy by driving. So its optimal route depends entirely on where the truck is going, and the problem must be solved jointly. Right now, the mathematical formulation. So we have inputs GST, where G is the graph with vertices V and edges E representing the road segments. Source vertices S from 1 to K and target vertices T 1 to K. Agents ATR is the truck and ADR is the drone. Then we have the cost and objective function. So edge costs, we have CTR of E is not equal to CDR of E. That is the edge cost of the truck and the drones are not equal. And objective is minimize the total travel cost for all agents, right? So solving the decoupling strategy. The problem is tightly coupled and intractable. So the stage one is getting to the truck perspective. That is, we route the trucks to be useful transit options where costs are discounted near the drone paths. And stage two is the drone perspective, where we route the drones over the composite networks, that is roads plus trucks network, right? So visualizing the composite solution. So we basically have this as the truck path, right? Let me show you. This is the truck path, all right. And we are basically going to deviate this to assist the drones, right? So we are deviating this path to assist the drones, and this was the drone path, right? Okay, so this is the drone path, and we basically be using the path where we are decoupling the trucks path and the drones path so as to optimize the basically the distance or the shortest path for the drone. The pivot from coordination to strategy. So in the previous section MAPF, a central brain dictated the movement of every agent. We now shift to scenarios where agents will be autonomous. So now we are talking about non-cooperative games, where these are basically games where the actions of individual players form the primitives. This contrasts with the cooperative games where joint actions of groups are primitive. So the anatomy of a game formulation is like this. We have players again, N, noted by N, strategies SI. Players are basically the set of decision makers, strategies are the set of actions available to player I, and utility UI is the payoff function mapping a strategy profile to a real number. Now, the goal is for each player to maximize their own expected utility. Now, rationality and best response. So, how does an agent decide? So, basically, they assume others are rational and play a counter strategy. What is the best response? A strategy SI is a best response if it yields the highest utility UI given the strategy profile of all the others, right? Now, case study is the prisoner's dilemma, which we have already covered in the previous video. The rules are if you confess alone, you get 1 year, that is a light imprisonment sentence, and the partner, your partner in crime, gets 10 years, which is a heavy sentence. If both of them confess, both get 5 years, and if neither confesses, both get 2 years. Right? Common knowledge is both players know this game, their payoffs, and that the other player knows the rules as well. Right? But they do not know whether the other person has confessed or not confessed. That is the main dilemma in the prisoner's dilemma problem. The payoff matrix we have discussed already. So if both the players confess, that is the ideal situation where they get 5 years each. Dominant strategy, equilibrium also. Now the paradox of rationality here, right? So the analysis is this is the rational outcome where both players confess and get 5 years each. So if player two or the prisoner two confesses, then and also player one should confess, right? Basically, if player two is confessing, then player one should also confess because he would be getting then from 10 years, his sentence would still be reduced to 5 years if both are confessing. If player two stays silent, that is, if player two is not confessing and player one confesses, then he would be getting 1 year instead of 2, right? So in both the cases, you see that he would be getting a better, you know, or you could say he would be getting a lesser imprisonment sentence if he confesses in both the situations, in both the scenarios. But the paradox here is that rational, intelligent behavior leads to a suboptimal outcome, right? 5 years compared to cooperation of getting 2 years, right? So system dynamics, coupling versus interaction. We have MAPF robotics. The challenge is physical coupling. Drone part depends on the truck, and the method is centralized decoupling. The outcome is post feasibility. But in game theory, in economics, the challenge is strategic interaction. Payoff depends on the opponent, right? And we have rational analysis based on best response, and the outcome is equilibrium, often suboptimal, right? So control versus autonomy. When we control agents, we fight computational complexity. When we don't, we fight incentive misalignment. And the core lesson is whether designing a drone fleet or market success depends on managing the interaction between individual agents and the collective goal, right? So that's it about the video, and thank you guys for watching.